And welcome again, Math 3 students, yet another exciting day of EDL learning. Today we're going to cover lesson 7.6. It's more with statistics, everyone's favorite. Okay, so today you're going to learn the basics of what we call inference. So, what are inferential statistics? Okay. The idea here is we're going to be using sample data to make inferences. Okay. If you don't know what that word means, it means we're going to make conclusions. We're going to use the data that we gather to try to make conclusions about the population. And you say, well, why would we do that? Well, a lot of times populations are so large that there really is no other way to do it. We try in America to do a census every 10 years. By the way, this year is one of those years. But even then, it's very costly. It takes a lot of time, and we never really truly get everyone's data. So typically, our only option is to take a sample. And then we use that sample to make conclusions or inferences about the population. Okay. So it could be about any population. It doesn't have to be America. It could be anything. It can be about bacteria. It can be about plants, animals, you name it. Okay, so that's what inference is. And it's used all the time in the real world. Pretty much any time a scientific study is done or a scientific experiment is done, that's what they're doing. They're using inference to figure out, hey, is this drug effective or not? Okay, and that brings us to one use of inference. It's called testing a claim. This is what you would be doing if you were experimenting with a new drug. You would be testing a claim. The claim, of course, would be that the drug is effective, and you're going to gather data and test that. Okay, so go ahead and read this example. Okay, and you could see we have some key information in here. So what I want to do is spot that key information. So right here I see sampled 30, so there's my N. Sample size of 30. I see standard deviation is right there, right? So there's my sigma. And now here's what's kind of new. There's two different numbers here for the salary, okay? One of them came from a sample, okay? And that would be right here, the mean salary or the average salary from the sample. So there is your X bar. Okay. So that leaves this other 42,000, right? This other 42,000, this is the potential true mean. You see, whenever I'm testing a claim, there's going to be some claim and then some other number, and those are the two numbers. And we're basically asking ourselves, is this sample of $43,260, is it far enough away from 42,000 to say, hey, 42,000 isn't right? Or is it so close that it was just random chance, right? It's like flipping a coin 10 times. If you get heads 6 times, you don't go, oh gosh, that coin's unfair. You go, oh, that was random chance. It's going to happen sometimes. But if you take a coin, flip it 100 times, and you get heads 99 of those 100 times, now you would sit there and say, whoa, something fishy's going on here, right? So that's kind of what we're doing anytime we test a claim. We have this 42,000 number. We think that might be the average. We have this sample that's higher, and we're asking, is this sample far enough away from that 42,000 to say 42,000 is incorrect? So here's how we do it. We get a z-score. Okay, so there's my X bar. Okay, and now we're going to say 42,000 is the actual mean. Even though we're really not sure, we're just going to kind of pretend, hey, if it is 42,000, how far is this away in terms of standard deviations? Okay, so 5,230 is my sigma, and then I had a sample size of 30. So that calculation right there will tell me my z-score, or how many standard deviations away from the 42,000 is this 43,260. Okay, so work that out. And we get 1.32 standard deviations away. Okay, so find that on our handy dandy table. And it's right there. Okay, but we want greater than, so we're going to do 1 minus 0.9066. And that tells me, okay, if the 42,000 number is the true average salary, there's about a 9% chance that my sample would come back at 43,260 or even higher, right? Because we just found all the area to the right. So about 9% of the time, random chance is going to spit out a number this high or even higher. Okay. So anyway, our z-score was 1.32. And the probability we got was 9.34%. That a mean of 43,260 or higher would happen by chance. Okay, now here's the thing about statistics. Okay, I'm not really solving an equation here. There isn't this exact 100% guaranteed conclusion. I can say that this happens with that frequency. But is that enough to go, oh, all right, the guy's right, it's over 42,000, or is that not enough evidence? Okay, that's what we're doing is when we test a claim, we're collecting evidence. And this is evidence. Is it enough evidence? Well, it depends. Obviously, the smaller that this number is, right, that means the further apart these are, and the stronger the evidence to say 42,000 is not the true mean, not the true center. Okay, so the smaller this, we call this, by the way, this is called the p-value or probability. Okay, so the smaller your p-value is, the more evidence you have that the 42,000's incorrect. Okay, the larger the p-value is, well, the less evidence you have. So how do I determine the cutoff for enough evidence? Well, a lot of times the problem might just tell you what the cutoff is, and if it doesn't, for now, this isn't AP statistics, so I'm just going to go the most common choice, and we'll just go with it. The most common cutoff is 5%. Okay. So if we have a p-value that's below 5%, we'd say, oh, we have enough evidence. We think the 42,000 just isn't right. But when our p-value is more than that, we say, we'll chalk this one up to random chance. It happens sometimes, so this is one of those times. And that's how a significance test works. Okay. When you take AP statistics, we'll be a little more formal about it. There'll be a little more work to do, a little bit more writing, but for our class, that should suffice. Okay, now there's one other type of inference we do. Sometimes we don't have a claim being made. Sometimes we're just interested in, hey, what do you think the center of this population is? Okay, and that's called a confidence interval. So instead of just reporting the mean and saying, oh, the mean of my sample is this number, we're going to give an interval. We're going to say, oh, there's a 95% chance the mean's between these two values. Or you might say a 99% chance the mean is between two values, right? So that's the idea of a confidence interval. Watch the presidential elections coming up. You'll see plenty of confidence intervals. They'll give polls for the various candidates, and then they'll say plus or minus a 3% margin of error, or plus or minus 5% margin of error. That is a confidence interval. So anyway, the definition of a confidence interval is it's a range of values that captures a parameter, oftentimes a mean, but sometimes a proportion or a slope or something else, with a given, I'm going to use the word probability. Well, if you take AP statistics, we'll talk a lot more about why it's not truly a probability. Whoops. Helps if I spell it right. Okay, but for this class, we'll just say captures it with a given probability. The most common probability there would be a 95%. Why do you think 95%? Because the empirical rule, right? That is a very easy thing to say, oh, about 2 standard deviations. So that's why we typically will go with the 95%. Okay. In order to calculate your confidence interval, you're going to take your sample, whatever you got from your sample. So I'm not going to say mean because it doesn't have to be a mean. It could be a proportion or a slope or whatever. So some sample value, and then you add and subtract a margin of error. So back to my example with presidential elections, you see a poll, it's not a mean, it's a proportion of people that say, I will vote for this candidate. And then plus or minus some margin of error. All right, so the formula, if I'm working with means, I start with my sample mean, then I add or subtract a certain number of standard deviations. Okay, so I'm going to say Z star. If I'm doing 95%, well, then this is about 2, right? If I'm doing some other percentage, well, then it changes. It depends, you know, how probable I want to be. Okay, and then that, of course, that's how many standard deviations. Well, it needs to get multiplied by the size of a standard deviation. So we would take sigma, the size for 1, sample size 1, and then divide it by square root of n based on whatever our sample size is. So over here, the margin of error, well, that's this bit over on the right. It's the amount we add and subtract. So my margin of error is whatever my number of standard deviations I want to go, multiplied by the size of the standard deviation. That's my margin of error for my sample mean there. All right, so let's try a problem. Go ahead and read number 1. Okay, picking out some key information. There's my sample size, 400. There's my sample mean, or X bar. There's my standard deviation. And then we have this new bit here, this 95% confidence. Okay, that is what's going to allow me to choose the correct Z star. Okay, so 95% confidence, I'm just going to use a Z star of 2 standard deviations, because remember, if I go 2 standard deviations in both directions from the mean, I'll capture about 95% of the data. Okay, so I now have the information I need. My formula is my sample mean plus or minus my Z star, the number of standard deviations I need to go to capture the amount of data they're asking me to capture, and then multiply that by the actual size of the standard deviation. So plugging this information in, I've got 68.4 for my X bar. My Z star is going to be 2 because I want to capture 95% of the data. And then my standard deviation for this, for a single person, is 20.9. But for a sample size of 400, I have to divide that by the square root of 400. All right, so there you go. That's a confidence interval. Go ahead and work it out. And we would get 68.4 plus or minus about 2.09. Now, whenever we do a confidence interval, we should actually write a sentence answer, because this problem has meaning, right? It has context. And that's why it says interpret its meaning. So we would say, we always start off with we are, and we restate the confidence. So we are 95% confident. The true, in this case, it's the true mean, because we're talking about means. So the true mean, and then what are we talking about? Mean of what, right? Here's where the context comes in. The true mean time adults watch TV on a weeknight is between, and then I go ahead and work this out, 68.4 minus 2.09, that's 66.31. Okay, and then the upper bound would be the 68.4 plus, right? So that's going to give me 70.49, and this is minutes. Okay, so hopefully you see that this is a little bit more useful than just saying, oh, the mean was 68.4 minutes. Well, once I add this extra margin of error, I can now see how confident I am. I can now say, wow, that's a pretty narrow range, right? So there's a pretty good chance that it's pretty darn close to that, 68 minutes. Okay, so that's how we do a confidence interval. Go ahead and take a look at number 2 and see if you can set that one up. Okay, so I read through the problem, I pick out the key information, and then I do my calculation. So in this case, my X bar, my sample mean is 2.6. I'm going to go 95% confidence, so roughly 2 standard deviations. I have a sigma, a standard deviation of 2.6 for a single individual, but my sample was for 224 individuals. And there's my calculation. So we work that out. And there's my confidence interval. Okay. And now I always end with a sentence, a complete sentence, restating the confidence level and putting it into context. So here we go. We are 95% confident the true mean or average number of school athletic events attended, and this was per year, is between, and again we work this out, that would give me 2.51 and 2.69. And there we go. Now, if you want more accuracy, you can get there. You would use a number that's slightly different than 2. You would actually use 1.96. But I'm happy if you just use 2. Also, I'd like to show you, again, if you have a calculator that does statistics, you can get a more accurate answer by asking your calculator to do the problem. So I could go into my statistics menu and say, I'm going to calculate, and if I, I'm going to do a test. If I scroll down, I will find right there what we call a Z interval. So if I choose that, and then if I had the raw data, I could just put the raw data in a list, but I don't. In this case, I have the statistics. So I can just plug in the information they gave me. Okay, so the information they gave me was a standard deviation of 2.6, a mean of, oh, I'm sorry, the mean was 2.6. The standard deviation was 0.7. The mean is 2.6. The sample size was 224. And I want to do a 95% confidence level. And there we go. And we can see that this is more accurate than what we had. But if we round this answer off, guess what? We still have the same answer. And that's why historically 95% has been the choice, because it's pretty easy to do without a calculator. You're not going to be perfectly accurate, but you're going to be close enough. Okay. And when you take AP statistics, you'll be able to do it with your graphing calculator. All right, next page. All right, take a look at number 3. Okay, now hopefully after reading these problems and circling the important information, you're noticing these are different, aren't they? Over here, this is what we were just doing. I have an N, right, a sample size, I have a mean, I have a standard deviation, I have a confidence level. That's what I just did. Over here is different. I don't see this sigma. I don't see an X bar. This is a percentage. Okay, so this is a different type of problem. When I have a percentage like this, we call this a proportion. So instead of calling it X bar, I'm going to call it P hat. So instead of a flat line, I draw like a little hat on there. And that's read P hat. So this is a proportion problem versus over here, a mean problem. Those are our differences. So a proportion versus a mean. Okay. And here we go. We're going to give you the formula for the proportion problem. We start again with whatever our sample gave us. Then we're going to add and subtract the number of standard deviations that we need to capture, in this case 95%, it'll be 2, but it doesn't have to be 95%, it could be some different number. And then it needs multiplied by the standard deviation. Now notice they didn't give me the standard deviation. And that's because they don't have to. You get to calculate it. Whenever you're dealing with a proportion problem, the standard deviation will always be the proportion multiplied by 1 minus the proportion divided by the sample size. And square root that whole thing. Okay. And of course this piece over here, the amount that you add and subtract, that is the margin of error. So when you see polls for the presidential election, this is what they're going to be doing. They're going to say, oh, 40 whatever percent say they're going to vote for this candidate with a margin of error of plus or minus 3% or 5% or whatever it is. All right, so let's go ahead and do the problems. This guy is going to use this new formula here. So the p hat was 0.57. We want to be 95%, so 2 standard deviations. And then the standard deviation is equal to 0.57 times 1 minus 0.57 over the sample size of 600. Okay, working that out. We would say 57% appear to be in favor of voting for this candidate with a margin of error of 4%. And a lot of people who don't know statistics, when they watch the campaigns, they see these numbers. But what they don't realize is a lot of times the numbers for the two candidates will overlap once you factor in the margin of error. So when that's happening, we call it a dead heat. We say that the results are currently within the margin of error for either candidate to win. And that's what has happened in some of our recent elections, and a lot of people get very upset by it. But it's just a matter that our accuracy is such that this could be random chance in our polls, that we're seeing the results that we're seeing because the poll results are just so close together. Okay, so anyway, back to the other question, the sample mean. That's what we had been doing. So that's 1.5 plus or minus 2 standard deviations because we're going for 95%. And the size of the standard deviation is 0.9 over square root of 600. So working that out, we get this. And there we go. Now I would normally write a conclusion for each of these, but I don't have a whole lot of space there. So how about this? I'll write the interval, and we'll actually just say the conclusion. We are 95% confident that the true proportion of students who want to vote for student A for ASB president is between 53 and 61%. We'll do the same thing over here. So we can say we are 95% confident that the true mean number of hours that a student spends each night on homework is between 1.43 and 1.57 hours. Okay. All right. So now what's the difference between the two types of inferences we did? Right. Remember, we started the lesson back here with a claim. We tested a claim, right? Notice that that's a little bit different. When I test the claim, I just figure out, oh, what's the probability of getting something this extreme or more extreme? And then I compare that probability to a cutoff, usually 5%. Okay. Versus the confidence interval, here there is no claim. We're just approximating the center of a distribution. Okay. And that's really the difference. So a confidence interval is simply approximating the center of a distribution. Okay. There was no claim, there was no argument trying to be settled. We were just saying, it's probably somewhere in this region that is the true percentage of people that are going to vote for this candidate, or the true number of hours that somebody's going to work on their homework on average. Okay. But a claim is different, right? When we're testing a claim, we're asking if a sample is so far away or so rare that we can make a conclusion. Okay. And now oftentimes the conclusion is, oh, we're concluding that this new drug treatment is effective against this disease, right? Or we're concluding that, oh, this average size or salary or time is not really the true average, or anything along those lines. So basically, we have some claim or argument, and we're going to settle it by looking at our sample data. Okay. All right. So that's the basics of inference. And right down here is where your homework starts. So enjoy doing the homework assignment, and I hope you enjoy inference, one of my favorite topics in statistics.